Welcome, everyone, to my presentation about functional programming and Kotlin. My name is Urs Peter. I have so much gray hair, that's why I can call myself senior software engineer. In my daily job, I try to be as much as possible with my hands in the dirt. When you get older, it might sometimes be a bit challenging because, well, this is where the real stuff is happening. I'm also a very passionate trainer at the XEB Academy, where I create a variety of courses, among other about event-driven architectures, where I had the honor to give a talk last year, but mostly about Kotlin. Also a Kotlin certified Japanese trainer, where I help teams in all stages of their Kotlin adoption, be it beginner, but also intermediate and advanced. Especially there's a lot to gain. When you look at my career, I started out with Java. About 10 years ago, I moved over to Scala. And, well, for the previous 5 years, I'm mostly writing backend logic in Kotlin. When you have gray hair, you can talk about 10 years, things like that. So about 11 years ago, I also gave a talk on functional programming in Java. In Scala, I did a lot of that stuff to the point where it made me sick. And in Kotlin, well, this is what this talk is about. That was about me. I'm also very curious about you. So, who of you is a Kotlin developer has developed in Kotlin? That's more than 50%. Great. Also good to see that maybe we have some Java people here, which might get to know what Kotlin can offer on that level. Who of you is using functional collections? So when you're Java developer using streams in Kotlin, that's just the standard library. OK, that's not that many. Great. So I probably have to tell you something. Who of you has heard the term monad? These are many hands going up. And who knows exactly what a monad is? Oh, that's much less. OK. We'll figure that out, that one too. OK, cool. So then let's right away hit the road and start our hopefully transforming journey, which has as an entry point the swamps of imperative programming. Well, there are swamps, right? Probably a place where you do not want to reside too long. But why is that? Well, if you would separate the programming styles into two large groups, we would come up with imperative programming. The sample here is a true example of imperative programming, which actually relies on declaring variables, which are then mutated along the way till you reach a state where return your result. Right? When you use Kotlin, you can fully do imperative programming using these constructs. So you would use vars, you would use loops, you would use mutable constructs like collections and objects, and here and there return statement. The second group would be expression-oriented programming. What is expression-oriented programming? Well, that's a way of programming where you think more in terms of functions that take some input, which is transformed to some output. And this output can, again, serve as an input. The example you see here is actually the same like on the left semantically, but then rewritten in an expression-oriented way. So expression-oriented programming is not yet functional programming, but it's definitely at the foundation of functional programming. The good news is Kotlin really wants you to program in this particular way, which we can see in the many language constructs Kotlin offers us. So, for instance, you would use the immutable features of Kotlin, which are very accessible to everyone, like data classes, vals. You would use immutable collections, which are default in Kotlin. So when you create a collection in Kotlin, it's immutable by default. In Java, it's mutable by default. You would use many expression constructs. So if you look closely, you see this equal sign and then try. So equals try. How is that possible? Well, even try catch in Kotlin is an expression, meaning it returns a value. So even try catch is an expression in Kotlin. Like if else, like the when expression, all expressions in Kotlin are expressions, not statements, so they return a value. And what you also would use are those higher order functions. So what's really fundamental about those two ways of programming is how we think about software. So in the imperative programming style, we think merely in terms of data mutations and automatically alongside side effects. Like doing a sort or adding something to a collection, return type is void. It's a side effect. Something happens at the side. In the expression-oriented programming, it's really fundamentally different. We think in terms of data transformation rather than mutations. So we think very strongly in this input and output thinking. So why would this expression-oriented way of programming be better than the imperative style? Well, there are various reasons for that. And once I personally started to embrace this way of programming, I really became a better programmer. Or in other words, I delivered better software, right? So why is that? Well, many reasons. For instance, just if you look at the amount of lines, it's conciser, it's more expressive. Why is it more expressive? Well, we actually program on a higher abstraction level, depicting our intent much clearer than in the imperative counterpart. So here we say we filter, we max by, which is a higher abstraction level, instead of having loops that just mutate stuff, right? So our intent is clearer because we use those higher order functions. Second, our code is getting very deterministic because we don't have side effects, right? So we have an input as an output, which is, so we exactly know what we get, which also makes it easier to test. When you get an output, you also can test for it. When you have a side effect, what are you going to test? You don't know. And what's also very interesting to see is that the scope of our operations is much smaller in the expression-oriented way than in the imperative way. So for instance, here you see we declare this variable defs on top. And then this variable is used throughout my code. So the scope of def is quite large, enforcing you to kind of scan through it, where is this def thing being used. In expression-oriented example here, we only actually have transformation. So the scope of one operation that changes something is the expression itself, having a much smaller scope than with imperative style. So reasoning about code is getting simpler with that. So should you not yet use this programming style, I really, truly encourage you, try it for 2 weeks. Try to step away from the loops and the variable declaration. You can also do this perfectly in Java if you want. It's maybe a bit more effort, but you still can do that. And I promise you, you won't be disappointed. Otherwise, you send me a mail. OK, so once we embrace the expression-oriented way of programming, I would say we moved away of the swamps to the fruitful valley of expression-oriented programming. Well, it's still a valley, right? There's probably more ground to be gained. So let's see if we can move on. Imagine we have this code sample, very dumb, simple example, where we save developers we fetch via some REST endpoint and save them to a file. And we save them in CSV format, very fancy format. So now a PO comes to your desk and says, OK, nice that you save it in CSV, but I want to have also support for TSV, tab separate value. You say, OK, the way I could solve it is by, well, copy-pasting it and convert it to TSV. We could do that. And of course, you all agree with me, this would be dumb, right? There is too much duplication involved. But how can we kind of address this in a more elegant way? Well, there's actually a very simple trick you can apply to come up with way better structures that would facilitate the reuse. So the first thing you're going to do is, if you copy-paste it, you look, OK, which piece of code are actually the same? Because this would become your so-called generic control structure. And then you look at the place that varies, and you look very closely. You look what goes in this place. So in this part, it would be a developer goes in, and what goes out of it, which would be a string, right? So developer in, string out. Once you know that, you can now define a so-called higher order function. Higher order function is a function that takes a function as an argument. So here we define this signature we've seen before, 2-line, a developer goes in, a string goes out, and then use it at a designated place in our generic control structure. And by doing so, we have a nice separation of concerns. So we have something that fetches developers and writes it to file. But how we want to write it to file is something we can define as a caller. So as a caller, and I can say to CSV, to TSV, to whatever format you want. And it's very surprising to see that in the beginning, I asked who of you using these functional collections, quite a few hands went up. So we use it quite often in context of collections, but in context of business logic, I do not see higher order functions being used often, even though they can be very, very valuable. So whenever you have some block that has a lot in common with another block, except for some minor changes, think of higher order functions. Another example would be with testing. That's also a very nice ground to play with this new paradigm. So what you see here are two tests, and well, a big part of our testing is creating test data and cleaning it up. Let's assume we cannot have some transaction and rollback and all that test is gone. Let's assume we have to really clean up our test data. Quite some things can go wrong here too. So first of all, it's duplicated. Second, maybe we forget to clean up test data, which might have an impact on other tests. So also here we can apply the very same trick. What is generic? Well, creating of test data and cleaning up. That's the generic control structure. We can make it even make a bit more configurable. So we have a count here, and we can say, OK, I want to create as many objects. So for our test, this would be helpful. Then the method of the testing would be the function, which just gets the developers we've created in our test data. And by doing so, we actually get two benefits. First of all, our test data will always be cleaned up. Second, we have no code duplication. Third, our tests get much more expressive because we now can really focus on what's the test about instead of doing all this coding for creating and cleaning up test data. So, should you not yet use this approach, if you have tests, try it out. Get familiar with it, and before you know it, you'll also use it for a business logic. So once we embrace these higher order functions, I definitely would say we moved on our valley to the abundant heights of higher order functions. Now we are quite high, but when you look around you, you still see mountains, right? And this is where you want to get. You want to go to the mountain with this beautiful view. So let's recap. The higher order functions we just created before do not have some sort of characteristics that we can combine them together and create new valuable results. So in other words, what we are missing is what we could call composability. We cannot compose it to new things. They're just kind of higher order function, and that's it. However, when we look at the very first example we saw in expression-oriented programming section, we see that collections have this capability, right? Collections in combination with higher order functions allow me to do a lot of chaining and come up with exactly the result I want by simply chaining the right building blocks together. So apparently, the collection container, so let's consider a collection as a container of elements, in combination with higher order functions, makes this possible. And now comes the interesting thing. So if we could figure out the fundamental aspects that govern these characteristics of composability, then we might come up with maybe different data structures that allow us to do the same beyond collections, right? So let's see where this goes. Well, this goes basically, this leads us to the realm of category theory. Who has heard of category theory? OK, nice. Quite a few hands go up. Category theory is the theory of mathematical structures and their relations. I personally like to compare them with the periodic table in physics, you know, where all the atoms are named. So category theory is similar to the periodic table in the sense that it defines logical building blocks. And as in physics, you can combine atoms to molecules, which have very different characteristics and traits. So category theory is also a kind of dissection of small logical building blocks you can combine to create more advanced logical building blocks. And as you can see, this is a mountain. And with a mountain, you can get very high, but you can also fall very deep. So it's a danger zone where all those fancy terminology comes in. So why is it a danger zone? Well, for a big part, it's because academia managed to describe these concepts in such confusing technology which you cannot relate to your real world, that only the terminology itself is a big hurdle. Can we blame academia? Not really, because category theory is not necessarily only for software development. It's just a very good field of applying it, but it's not necessarily only for that. It's wider than that. But as said, because of this terminology, you have quite a few developers that stand at the foot of this mountain and they look up and they just see the fog. They think, okay, let's get away. Or you have the bold ones among us, say, okay, I'm going to climb that mountain, I'm going to go through that fog. And then eventually you stand at the top, having this beautiful view over, that reaches very far. But at the same time, you're very detached from the real world. And it's cold and lonely up there. And I think in both cases, we fail to unlock the promising opportunities and possibilities that lie within these concepts. So for the rest of the presentation, I will try to do my best to demystify many of these complexities in order to extract the valuable parts in it. OK. Not all hands went up in the beginnings when I asked, do you know monads? The good news is we all know monads. Probably have not really be conscious about it. And you even use them daily. The way I like to look at monads is compare them to containers. When you go to a container haven, well, there are many containers, but you have different kinds of containers. You have normal containers, you have air-conditioned containers, you have fireproof containers. So they're all containers, but they have different traits and characteristics. So, and the same, to a certain degree, applies to monads. The container we're going to look at first, which you all know, is, again, collections. And then there will some others introduced too. So from a container perspective, not necessarily looking at collections themselves, but from this container overarching perspective, which kind of operations are interesting in the context of collections? Well, what we can do with collections, for instance, is we can combine two collections. Right? So you have a container with some elements, you have another container with an element, and you combine them, and then you get a new container that contains all the elements in it. If you have this capability, in this category theory lingo, they would call this a monoid. And that would be the interface. It's even more complex than that. There will also be a semi-group, but just let's make it not too complex. For us, it's for now a monoid. I personally would have preferred the term a combinable. That's something I could have related to, but monoid, come on. OK, that's the way it is. This is the monoid. Second, if you have the capability to transform values, that's what you can do with a map method in collections, right? We have a collection, we take every element out, we apply certain function, and then we get a new collection with transformed elements. If you have this capability, then it would be called a functor. This would be the interface for a functor. Also here, maybe a mappable would have helped me, at least. Functor, what is a functor? The third one is probably the most powerful one, the interesting one. So imagine we have this developer, and developers have languages, and what I want to know is all the languages of multiple developers, right? So if we use the map method, well, I would end up with lists of lists. I don't want a list of lists. I want to have a list with languages. And this is where basically flat map comes in, which does two things. It maps, and it also flattens out this additional layer. So when I have a container, I take out an element. And in my flat map method, I have to create a container of the same type, so in this case, a collection with elements, which then would not simply be mapped like in map, so that you get containers of containers. Now, the additional layer is simply flattened out. That's where the name flat map comes in. And if you then would combine all the three characteristics, monoid, functor, and the flat mapping, then you would have your monad. There we are. So, monoid part, which I call combinable, or which would have helped me if they have called it combinable. The functor, so the mapping part, then the monad. And I think a composable would help me too, because it allows you to compose things. So we've seen collections are monads. And, well, you know even more monads, like an optional. If we try to identify if something is a monad, we have a special language for that. So we could say a optional models the effect of optionality. So models the effect of are here the keywords we need to use. And we'll see why this is important in a minute. So is an optional a monad? Yeah, let's check if these methods we defined here on the left are available in optional. Can I create an empty optional? Oh, I can. I get an empty, right, or a none. Can I map a value of an optional? Yeah, there is a map method. But interesting thing here is that map fundamentally behaves different than in the collections. So map would only kick in if my optional would have a value. If it was empty, it would simply be skipped. So the effect is different, but it's still a map method, right? That's the kind of switch. How about flat map? Sure, there's a flat map. And flat map ensures me that if I create another optional in flat map, I wouldn't end up with optionals of optionals, but simply an optional. So we can tick all boxes and say optional is a monad. Who of you has done some reactive programming? Not that many hands, quite a few. Well, then you most probably also encountered these building blocks, the futures, the different names, complete with futures, observable, uni, mono, all frameworks have a different name for it, but they do exactly the same. So what do they do with the definition we just learned before? Well, a mono from Reactor Spring Boot, that's why I showed, most probably it's well known, models the effect of latency. Right? So a future, what it can do is it will give you a value or an exception eventually. So not right away, but eventually, once, for instance, you do some network call, you get a reply back, then you would get either a value or an exception. So it models latency. Is it a monad? Let's do the check. Can you create an empty mono? Yeah, I can do that. So let's assume I have these two calls I would like to make. So get developers by name, which will determine mono, and then select best language. If I would use map, what would map do? Well, map would be called once I get a reply back from the service call to initiate the next action. So the effect of map is fundamentally different from optional or collection, but it's still map. And where would flat map come in? Well, if I would try to do these calls sequentially, I would like to call these two methods sequentially, well, then flat map would be my friend. So flat map would kick in once I get a reply from the first one, then I initiate my next call, which again would give me a mono back, but instead of having monos of monos, again, I end up with one mono. So it's an optional. It's a monad. So what are these abstractions and confusing terminology good of? The terminology and the confusion, I think that's absolutely useless, but what these monads offer us is something very valuable, which is composability. And because we have now heard of this new concept, of course, as developers, a curious being, we want to throw it at our problem, see if it maybe helps us. So why not make our error handling a bit more composable? If we look at these try-catch blocks, I mean, the real discrete blocks doing their own thing, that's not composable code, right? So let's see. If I want to make something composable, what do I need? Guess what? I need a monad, right? No composability without a monad. Which monad could I choose? The good news is, in Kotlin, we already have a monad in the standard library, which is result. These are the most important methods of result. Result is a very simple type that either contains a value or an exception. Not like a future, which eventually has one. This one is much simpler. It's just a wrapper, basically, that has either value or keeps the exception. That's it. And we see that it has a map and a flat map method. So what do we have to do to convert this piece of code using a monad? This is how this goes. I would use run catching. That's also a standard library in Kotlin. Then you could feed in the part that might throw an exception, and from there on, I could use my composition logic. So I get a more composable way of doing things. I think he has a good point, right? I have this client get devs by name and another client method. How do I know that these methods throw exceptions in the first place? I mean, it's not in the signature. Basically, Kotlin only has unchecked exceptions, so it's in no signature at all. There's, of course, a reason for that. But let's now kind of assume we are very puristic, right? Whenever I have an interface, I want to really know for sure what's in the signature. This is where many functional programmers that go to the edge think of code. Okay, let's assume that's a good idea for now. Then I could say, yeah, I really want to be explicit about my return type, so I'm going to convert this signature into result of a certain type. So I know for sure that I can expect an exception and can act accordingly on it in a composable way. And if I would do that, well, this is the code I would end up with, always returning results of everything, and then be able to compose my way out using these methods. OK, so now let's go on to a larger sampling, see how this would scale. Right? It's always nice to have a snippet, but interesting. It often gets very interesting when you see how these constructs scale across more lines of code. If I only had to call these 3 services in sequence without any exception handling at all, this is the code I would end up with. And you see, there's a lot of flat mapping involved. Because I said I get a result, and I don't want to have a result of results. This is where flat map comes in. So flat map reduces this additional layer that would be introduced if I would use map, for instance. And, well, maybe you now know what flat map is, but maybe your colleague, which has not heard of these concepts very thoroughly, might have an issue with that. So the question is there maybe a more convenient way to deal with these kind of monadic abstractions? And if we ask this question to us, then we will definitely encounter this particular library, Arrow. Who has heard of Arrow? OK, about 10, 20%. Cool. So Arrow is a beautifully crafted library. I really consider it a jewel of the Kotlin ecosystem that tries to bring a functional programming in a very idiomatic way to Kotlin. So many of these concepts are there, but kind of wrapped in such a way that they do not feel like too much of this functional, do not contain too much of this functional purity, which might be confusing. They contain many low-level monads, like option, either. Either is a very important type. Either is a bit similar to result, except that it simply has a left value and a right value. And what you do with left and right, that's really up to you. It is common practice to use the left one as some sort of error condition and the right one as some good condition, but it's up to you. So it's said similar to result, but what kind of types you define is something you can define yourself. IOR, which has left, right, and both. So for instance, may have a successful result, but one also give back a warning. These kind of things you can model with it. But you also have higher order monads, like resource, retry, circuit breaker, even sagas, all leveraging this monadic concept. Definitely worthwhile to take a look. And we will do this also in presentation. So what Arrow actually introduced is a kind of building block you see in hardcore functional languages like Scala or Haskell, which are monad comprehensions. And monad comprehensions are actually a way to avoid flat map. That's basically what it is. And in Kotlin, it would look as follows. You would have this result, so-called comprehension, which is kind of code block which allows you to do other code. In Kotlin, this is called a function literal with receiver, a very fancy name for that. And what you can do here is instead of calling these flat maps, you would call bind. What does bind do? Weird word, right? Bind. It's actually quite simple. If I have an OK value, bind would simply give me back the OK value. If I would have an exception, then it would return, so this whole construct would right away return a result with an exception. So at the first encounter of exception, it would simply return the result with an exception. And by doing so, we can focus on the basic flow and not having to nest our code like here above. And as said, bind is maybe still a bit, but up to you to decide. But I like this piece of code better once you're a bit more familiar with bind than this nested flat mapping on top. OK, and with the advent of context receivers, that's a language feature which is in preview for quite some while, but might make it to Kotlin 2. You can have even nicer signatures that actually use the same concept. So then you would have the context receiver for the bad return type, but it's still in the signature, right? It's not like an exception that you must know of to catch it. It's still in the signature. But the main signature kind of really depicts the basic flow, the object we really care about, not the alternative flow. So stay tuned for context receivers. OK. Now, so once we've tasted this power of composability, let's apply to real-world examples, because this is not real world, right? This is much too simplistic. In a real world, well, I definitely need some reactive abstraction, a mono. And yeah, sure, I want to be explicit about my return types, having a value or an exception. And well, why not also introduce option to make it even more clear that I can have a result or not? OK? Let's see where this ends. This enthusiastic start. So if you would have to write code that simply calls all these three services in sequence, this is what you end up with. And every flat map and map, they're just all the same names, but they have, as said, different effects, depending on what you call it. And you might agree with me that this is no fun. So should you find yourself writing such code, then I can congratulate you, because you managed to convert your code base into a container terminal. And you know where you are? You're here in this crane shifting around containers instead of writing business logic as you're supposed to. And believe me, I've been there, done that, and I'm not going to go back. In Scala, this was what I often encountered. So you might ask, hey, we've seen these fancy constructs, monad comprehension, maybe they can help us. Sorry, they only work basically for one monad. Then you have even more advanced concepts like monad transformers. And what they do is they allow you to convert a combination of monads, so the inner value of a combination, right away. So instead of calling map map, you would be able to call map t. Does this work? Well, they only work for 2 levels. And there's also no syntax support in Kotlin for that. And anyway, I really promise you, you don't want to have these kind of methods in your code, because it's just a nightmare. So, in my real-world example, I really want to have these kind of abstractions. So can I maybe bring it back to one monad? Would that be possible? The good news is, yes, you can. When you use Kotlin, so who of you has used Kotlin with a reactive framework, like Reactor? Few hands go up. OK. Well, then I can assure you, you probably suffered a lot of pain without that much gain. Because Kotlin has coroutines. That's a beautiful abstraction which allows to reactive programming, which is kind of built in the language itself. So you define your code as if in your blocking code, but then the language itself would figure out the asynchrony. So the mono really can throw away in favor of suspend methods. One monad less to go. How about option? Well, Kotlin has nullable types built in the language, so why would you use optional or option? Not needed in Kotlin. So now we're back to one monad, still having the features we want, and then, well, our code gets kind of doable. Still have a bit bind, some of these lets, and maybe if you're really new to Kotlin, this looks like, whoa, what is this? But I can reassure you that if you program Kotlin for a month, you're much more familiar with these constructs. OK, so by now, I think we kind of explored this lonely peak of monadic mist, and it's probably not yet a very nice conclusion of this talk, right? It feels a bit moish. That's, of course, up to you. At least that would be my personal evaluation so far. So I think the important question is, which amount of monads is OK? Which brings us back to a much wider question, which was also in the keynote was addressed: what is good code? Well, many books have been written about good code, and many books will be written about good code, right? In my stance, it's actually quite simple. You have good code when it reflects the domain you're in as clearly as possible. So when you're a pet shop, well, your code should be about cats and dogs. When you're a bank, it should be about mortgages, saving accounts, and so on. So in other words, your code should contain a minimum of non-domain abstractions. And if you have non-domain abstractions available, they should serve a very specific, valuable purpose. And you can kind of verify that with maybe someone who is not a programmer. If he can kind of read through your code and understand from a domain perspective what's going on, I think you've done a decent job. But when it's just about flat mapping, probably he won't do that. In other words, if your code looks like this container terminal, then you screwed it up. For one exception, if your company is a container terminal, then it's fine, right? But only then. So what we're going to do now is we're going to look at what happens if you just blindly throw monads at everything. And in this particular case, the result monad. How does this affect the layering of your application? Using a standard layered architecture, so no hexagonal, but it would more or less end up the same way. And we have some data access layer with some database calls in our data access object, some API we're calling. Then you have a service layer that does some business logic. Eventually, some API layer, assuming a standard Spring Boot application. And yes, you can use suspend in Spring Boot application. That works. And of course, some exception handler that would kind of accept or catch all the fall-throughing exceptions and deliver a REST reply. So in this case, we decided to let's be explicit, let's be puristic. So every interface should have a monadic return type like result. And if you analyze it, what you see is that basically we just passed it on and on and on and on till we reach the controller layer, the API layer, and then throw it so that the exception handler can do its thing. Well, does this add a lot of value, this abstraction? I doubt it very strongly. So let's see what would happen if we simply would not do it. And probably in 95% of all cases, that's perfectly fine. Just don't use it. 95% of all cases. Of course, you always have the 5%. Let's see. So in our basic flow, we don't need monads. In the case where you just get an exception where you cannot recover from, so there's no connection to your database, yeah, what do you want to do? Well, you throw your exceptions. Not interesting. It's getting interesting in cases, like for instance these, where you do some API call, where you might recover from. So if you can recover, then you ideally must have a way that tells you, hey, this API can throw these errors and make it easy for you to handle these errors instead of assuming, there might be an exception. Which exception again? I have to look in the source code. No. In the signature, I want to be kind of attended that this is what you can expect back. Do your thing with it. So I might recover or not. So this means that, for instance, for database access, why would you use monads for database access? Either you get stuff from a database or your connections are there and don't get anything. So using monads there, I just would not do that. But if you have some API you would call from which you could recover, it might be value to use some monadic type. I would not use result. Why? Well, result gives you exceptions in case something goes wrong. And using exceptions to define your control flow for alternative cases or to recover from is maybe not the best approach. So I would use either with a clearly defined error type, maybe some sort of sealed interface. You might have heard of this approach also in Java by now, that allows you to kind of really know all the possible cases you should be able to take care of. And then, in the calling part, as said, I'm kind of forced to deal with the alternative cases in a very explicit and deterministic way. And if I have to do that, I think there it is valuable. In case I still have this fall through, I simply would then say, okay, in case I cannot recover, throw and then let the default mechanism kick in. And this is, in the projects I've done so far, actually, I've seen this approach being really the most successful. I've gone both sides, so hardcore functional with the container terminal to this, and in my case, this kind of approach has really paid off. Okay, so once we come to the realization that this functional programming is great if you apply it selectively, then it's a good thing it's a very valuable asset for creating beautiful software. So for the rest of the presentation, I will go through some examples of Arrow, where I show you some cool tools that might simplify your life tremendously. Let's look at this example. So it's kind of a factory pattern, right? I get some attributes and I have to create a Kotlin developer out of it. And there is some validation involved. So here I do a lot of null checking. I do even some conversions from a string to an int, so to int or null. So if it can convert to an int, then it would do that. And then I create my Kotlin developer. But there's also some duplication involved in the transformation of my value, right? So here, for instance, the age I have to convert here again, and a lot of if-else logic. It's nice that Kotlin has this smart casting. So if I checked for null, it knows it's not null anymore. So that's kind of a nice thing of Kotlin. But is it the most elegant code I can think of? I don't know. Arrow offers us a nice comprehension, which is nullable. Nullable has these bind methods, and they do exactly the same thing like before. So if one of these values would return null, then the whole answer would directly be null. So without an if statement, you can compose such logic in a very simple and accessible way. Okay, maybe you don't want to just have null back or a developer if your input is not correct. Maybe you also want to validate it. And in validation, these monads can also add quite some value. So this is an example of not having monads, right? And what we want to have here is a bit of an advanced validation. We want to accumulate all the errors instead of just stop at the first occurrence of a validation error. No, we want to know all the things that are wrong and then return it somehow. So there are quite some issues with this code. First of all, again, the conversion I have to do twice. So is null or empty, that should be a nullable string. So then I have to use this exclamation mark here, which is kind of code smell in Kotlin. Don't do that. I also throw an exception here, which I don't know if if it's okay that's such a generic exception and I would handle it, but maybe sometimes I want to know whether it succeeded or not. And then I really have to go into the source code and look at the Kotlin docs to see whether I get an exception or not. Also here, Arrow has a beautiful building block, which is called zip or accumulate, which does quite a few things at once. So in all those lines, I do actually two things. First of all, I convert a certain value to a certain type, null or not null, and then also validate it. If it's not validating, then I give here actually the error type. So here in this block, you would define the error type that would be accumulate automatically for you. And then once all conversions and validations have passed, I get in this function here all the values that I've converted and validated. So within here, I'm 100% sure that all those values are exactly in the condition I validated them for. And otherwise, all the errors would have been accumulated for me. If I then would use a context receiver, you don't have to, but that would make my signature even nice. So I would get back a Kotlin developer or then a list of validation errors, which I will really have to take care of when I call this particular method. And I said, maybe that's a bit overwhelming if this is the first time you see this piece of code, but once you start to play with it, you will definitely see that it's a very elegant way of doing something to a certain degree complex, like validations that involve conversions and so on. The third one is also an interesting capability, which is part of functional programming, which are optics. Imagine we have this kind of tree or object hierarchy, which is quite nested, right? So we have a developer has a language has some statistics, and we would like to change the popularity of the statistics. In Kotlin, you have this beautiful feature of data classes with copy, so you can kind of create new instances out of new immutable instance of an existing one. I think the biggest feature is missing in records in Java. But when you want to do this in a nested structure, to get to the leaf, like here, is quite annoying because you have to copy all the intermediate layers, right? And when you have deeply nested structure, that's kind of a pain. Optics can also help you greatly there. So what you do is you would simply define the path to the place where you want to be in your object hierarchy, then pass in the instance here, and from there on you would get directly the leaf you want to change. You won't get this totally for free. You have to annotate it and have some symbol processor in your build, but that's just a matter of configuration, and then it would work. So if this is a case where you might suffer a bit, this might also be in tests, for instance, because in tests we often create some data and then want to just see how it does in a certain context. That might be also a very good outcome. So once we've realized that functional programming is not an all or nothing solution, then I think we've entered the prosperous alpha meadow of functional common sense, which is a solid ground, which is still approachable by many people, and which allows you to, if needed, use or pick those functional assets, but not kind of overload your code with the rest. Thank you.